I just took a swig of Coke because I needed it. The eye. Okay, Dan. Well, what do you usually think about from Dan is questions that would come right from Montana. So let's just kind of look at this as if we were all sitting in Montana along a trout stream, I guess. Here we have the cornea. Most important thing about the cornea is what? Well, it's protective, but it also, that's where the greatest refraction of the light occurs. That would be the question you'd really have to be careful about. It's not the lens. The advantage of the lenses is that you can control it. So up in here we have the anterior chamber. I don't think anybody missed that. It's full of aqueous. Then we got the posterior chamber. I think people might confuse the posterior chamber with this back here where the vitreous is. Okay, then you have the iris, okay, controls the size of the pupil. And we have all the stuff, what I would call associated with the ciliary body. You got the muscle, and then you also got vascular systems in here that produce the aqueous. So the aqueous would just go up into this posterior chamber, through into the anterior chamber, and then go out through the trabecular network and here out the canalis phlegm. Okay, what else can we see here? Well, we see the optic disc, and we can see the fovea here. And of course, this fovea we'll talk about later, but you know, most of the layers have moved aside here, and the cones are right in here looking at the image. I might ask you what this is, whether this is a right or a left eye. And here's the disc right here, so this is the left eye. Here's the retina. We're going to look at all the layers of the retina. So the image comes through the anterior chamber, the lens, through the vitreous humor, all the way back to the retina. Ganglion cells are inside, photoreceptors are outside. This would be inner retina, this would be outer retina. Now, the first thing I want to talk about is this ciliary body, these muscles in here. Now, normally, if we're looking at something over 20 feet away, there's going to be a lot of tension on these zonial fibers. So this lens will be flat, okay? So then as we accommodate, these fibers will contract and take the tension off these zonial fibers, and the natural tendency of the lens is to round up during accommodation. So how can we do that in this slide? If we want to round up that lens, we start the information out of Edinger-Westphal. You all know this. These are preganglionic parasympathetic fibers that go out to the ciliary ganglion. From the ciliary ganglion, they're going to go in the ciliary nerve, and they're going to go into the muscle. And then once the muscle contracts, the lens will fatten up. Now, this really shows it pretty well. Right here, you can see a lot of tension on those zonial fibers. So this is a normal situation. And you can see it's flattened. This lens is pretty flattened. Then, if you release the tension on these zonial fibers by contracting the ciliary muscles, the lens is going to have a natural tendency just to round up. So this would be when things are moving towards our eye and we want to accommodate so that we can read. This just shows a couple things that we just talked about. Normally, you know, things will be focused right on the fovea. Now, if you start to move closer without rounding up this lens, the image would be focused behind the eye, but if you can accommodate, you'll bend those light rays so they end up right on the fovea. Now, in an emmetropic eye, okay, things are going to fall right on the fovea. Myopia, which I have, my eyeball is too long. I probably have some problems with my cornea. The image falls in front of the retina, okay? So I can see things up close, okay, so I'm nearsighted. Hyperopic eye, the eye is too short, and the image falls behind the retina. And these people can usually use their lens to accommodate, okay? But they can see things far away, so they're called farsighted. Now, next thing I want to talk about would be right here, the iris. Remember, this is going to control the size of the pupil. And this has a parasympathetic and a sympathetic innervation. Here it is right here. Now out here, these fibers out here are going to constrict. Actually are going to make the pupil smaller, okay? These are going to make the pupil smaller, and these right here are going to make the pupil larger. So the ones that want to make it larger are which? Are they the sympathetic nervous system going to make it larger? Of course. Which one's going to make it smaller? the parasympathetic nervous system. Parasympathetic input is going to constrict it, constrict the pupil. And remember, the parasympathetic is going to constrict the pupil, and it's going to do it via cholinergic mechanisms. And the sympathetic system is going to dilate the pupil, and it's going to do it via noradrenergic mechanisms. And one thing that really helps when we make that pupil a little smaller, it helps us with our depth of field, and it can take a large blur circle like this and make it much tighter on the fovea. What else? Well, we can talk about the optic disc, all right here, or we can talk about the fovea. We talked a little bit about the fovea, okay? You can see it right here. And you all know that this is the area of best vision. A little bigger area where there are lots and lots of cones all through here would be the macula. And a lot of people use these interchangeably. But here's the retina. And this is the inside. So here you can see some ganglion cells. Okay. So if I was to ask you which way is the optic disc here, would you say this way or would you say this way? And you'd be right if you said this way. Here the ganglion cell bodies are about 1 million of these, and here are the axons running on the inner side of the retina. This is inner, this is outer. Then we'd come to some of these cells right here. All right. These would be your bipolar cells. And then you come to these cells right here, which are the receptors for these are rods and cones, okay? Out in here, you'd have the retinal pigmentum epithelium right here, which is kind of interdigitating here with the outer disc of the rods and cones, and then you have the choroid, which you can see is pretty vascular. You should know the difference between rods and cones. Dr. Ulrich likes that. I don't know if you'd have to know there are 120 million rods, but you already do. 6 million cones, you know that. These are for night vision. These are for day vision. They have color. These are going to be more at the fovea. These are going to be more at parafovea and out peripherally. The cones have pretty direct connections. So one cone would go to one bipolar. Rods, they're not. They're pretty sensitive, but they don't have direct connections. So one rod, lots of rods are going to converge on one bipolar. Again, rods you can't see color with. Cones you can see color with. This just shows their distribution on the retina. Again, around the fovea, you're going to have lots and lots of cones, pure cones. As you go out here peripherally, you're going to have more rods and cones, and everybody knows the old story here. In parafoveal vision, you use this to look at stars at night because the rods are pretty dense right here. Okay, so fovea, pure cone, more peripheral you go, more rods. Here's the optic disc right here again, and here's the fovea. I wanted to show you a picture of this. Here you can see the ganglion cell layer right here. You can see it doesn't go into here. So this image coming right in here is looking right at those pure cone receptors right here. So I would say all this area in here could be the macula, but I think it's okay with me if you use the term fovea and macula interchangeably. Just know that out in here now, this is going to get blood supply from the central retinal artery. This down in here is going to get blood supply from the posterior ciliary artery. Remember, there's no blood supply in here. If we turn our attention to the optic disc, the main thing you probably are thinking about is cupping, glaucoma, but let's take a look at it. Here you can see the central retinal artery and vein going through here. You can see right in here this posterior ciliary artery getting the retinal pigmentum, the pigmentum epithelium, and the outer parts of the retina. Remember, the central artery and vein is going to go in here and get the more inner parts of the retina. Don't forget, as the axons from the ganglion cells come in here, they're myelinated. But when they're still out here, they're not myelinated. They become myelinated when they come into the optic disc. Don't forget, the cup will get bigger, will get much bigger in glaucoma. Okay, so keep thinking about that. A little bit about retinotopic organization. The way I remember it is the right half of the visual field always falls on the left halves of the retina. So the right visual field will fall on the left halves of the retina. So in this eye right here, it'd be nasal retina. And this nasal retina is looking from here to here. In this eye, the left side will be temporal retina, right here. And it'll only be looking from here to here. Okay? So keep that in mind. Okay, and don't forget that this nasal retina right here is seeing a lot more of this field than this temporal retina right here. So again, the temporal retina sees from your nose out to here. This nasal retina right here sees all of it on the same side as the retina. Now you know that the nasal retina, okay, here's your nasal retina, which is looking at the temporal visual field. These axons cross. Temporal retina right here. Okay, this temporal retina is uncrossed. Okay, this temporal retina is looking at the nasal visual field. This nasal retina is looking at temporal visual field. So if we get back in here, in the optic tract or in the lateral geniculate body, you're going to lose the contralateral half field. Any lesion in here I'll call contralateral homonymous hemianopsia. You have a lesion in this area right here, I'm going to call it bitemporal heteronymous hemianopsia. Now, if you lost this right here, think about what your real visual field loss would be. It'd be a bitemporal heteronymous hemianopsia. And you're only going to be looking with your temporal retinas. So you're going to be able to see pretty much in here. You're just not going to see out here and out here. Well, everybody should know this is a lateral geniculate body. If you don't, you're in big trouble. This would be the left one, actually. And you can see these different layers in here. Now, you should know what projects to the lateral geniculate body. And you should know where it projects. And you should also know what happens with lesions of the lateral geniculate body. So remember that both retinae project to this. Okay? Both retinae project to this. So that would mean that the structure as a whole receives input from both eyes. But the retinae project, each retina projects to only one set of layers. So this might be ipsi contra, ipsi contra, ipsi contra. You don't have to know the real organization. But the structure as a whole is binocular. But the layers, the cells, receive only input from one eye. So we would call them monocular. So again, the cells of origin of axons that end in the lateral geniculate are the ganglion cells. Now, where do these cells in the lateral geniculate project? They project via the optic radiations, the retrolenticular limb of the internal capsule, to area 17, and only to area 17. They don't go any further. They don't go to 18, 19, 20. So to get visual information to area 20, you've got to go to area 17, and then from area 17 to maybe to 18, 19, 20. All these cells project only to area 17. Now, if I had a complete lesion of the lateral geniculate body, I would say I had a contralateral homonymous hemianopsia. I would have absolutely no problem with my pupillary light reflex. Absolutely no problem with my pupillary light reflex. And this shows some of the retrolenticular limb of the internal capsule here. Okay? So all these axons have started in the lateral geniculate body, and they're going back to area 17 here. This is area 17. Most of area 17 is on the medial wall. Here's a corpus callosum, okay, cerebellum. Here's a little fissure here. Some people call it a sulcus, but I call it a fissure, calcarine fissure. And there's a little gyrus here, I call this lingual gyrus and cuneus. If you haven't learned those terms, I guess Dan doesn't think they're important. That's okay. Main thing is that information, this whole area here, is looking at the contralateral half field. Contralateral half field. So if you wipe this whole thing out, except in some cases where you might have a little macular sparing, you're going to have a contralateral homonymous hemianopsia, just like if you wiped out the whole lateral geniculate body on this side. The interesting thing is that the contralateral half field is mapped, interestingly, on this area 17. Down in here, in the lower part, this would be ventral, this would be dorsal, this would be upper and lower. I know we use both terms, so you could call this ventral and dorsal or upper and lower. Down here in this lower part, the upper field is going to be represented in the contralateral half field, upper. When you go above the calcarine fissure, the lower part of the half field of the contralateral visual world is represented. Now, a very famous pathway terminates in here called Meyer's loop. Meyer's loop. It goes to the lower part, below the calcarine fissure. So you're going to have an upper quadrant problem, and I'll talk about that later. But you should know Meyer's loop. Now, the opposite half field is also mapped on here in retinotopic coordinates. Central vision is back here. Peripheral vision is up here. So you should know that. Peripheral, central, upper, lower. Blood supply to this area, without a doubt, posterior cerebral. You should know that. Again, I'm showing this right here. See, he's got a calcarine sulcus. It's pretty big, so I might call it a fissure. Okay. This is area 17 back in here. Then you got 18 and 19. Now remember, the lateral geniculate projection does not go beyond area 17. Okay. So when you have lesions out here, 18, 19, they're very what we would call higher level visual deficits. You're not going to have a scotoma, a black spot. You're going to have higher problems, like all there are areas out here involved in motion. So you might have trouble, knowing that the car is coming at you, or even see the tea going from into the teacup. But that's something I would call a higher visual problem. The scotomas, the black spots, are only going to be if you get this area right here, area 17, which is the target of the lateral geniculate body. So input comes in here from the lateral geniculate. Then it farms it out to these higher areas. But it only goes to here. On the medial wall, again, the blood supply here would be posterior cerebral. If you don't know any vision, you should know this one. A, of course, you're blind in the ipsilateral eye. That's pretty good. You should think about, if you're shining a light out here, with this lesion here in A, would you have a relative afferent pupillary defect? Of course you would. If you have a lesion at B, you get the bitemporal heteronymous hemianopsia. Everybody knows that. You could have a little pituitary lesion pressing on that. You probably won't see this unilateral nasal hemianopsia, but you maybe a little problem here with your internal carotid as they're coming up in here. You're only going to get these fibers from this temporal retina and damage those. I think this D is probably the most popular one in the course. Contralateral, or if you're on this side and it's the left, would be a right homonymous hemianopsia. Homonymous because you can see both the deficits on the right side, homonymous. This would be a heteronymous this one would be heteronymous for me because this is on the left and this is on the right, but I wouldn't worry about that. Now, right here, right upper quadrant hemianopsia, or a right upper quadranopsia, you could call it either, is E. Now you can see that's Meyer's loop. Now don't forget, it's upper quadrant. Meyer's loop kind of loops out there in the temporal lobe, and it's easy to get those fibers. And here, remember, they're coming to the ventral bank, and I use the term lower bank. So this is underneath ventral to, or lower than the calcarine fissure. And of course, there are other fibers here at F, okay? If you get those, you're going to get the opposite of Meyer's loop. You're going to have a right lower quadrant hemianopsia. And if you get them all coming back here, it's pretty comparable to having a lesion in the lateral geniculate. Again, it's going to be a contralateral or right homonymous hemianopsia. And you read in the book many explanations for this macular sparing. We talked a little bit about the relative afferent pupil defect, and I think everybody probably knows this. You shine light into this eye, okay? It can go to both pretectums, right back here, and each pretectum goes to both Edinger Westphals, and out you go, up to the ciliary ganglion, and then you go out to the iris. So if we had lesions, if you shine the light in here, you get constriction of both pupils. If you had a lesion of the optic tract, of course, you shine light in here, what do you think is going to happen? Shine light in here, the amount of light getting here is a lot less. But if you swing over to this one, you're going to get a lot of light and you're going to constrict. So the irises are going to go constrict, a little bigger, constrict, a little bigger. So as you swing the light back and forth, you're going to get a change in the size of the pupil. And that can only happen if you have a big retinal detachment or something wrong with this retina in here, more than 50%, or if you have a lesion of the optic nerve. Anywhere else back in here, you're going to have an equal amount of light coming in from the two eyes, and you won't have a relative afferent pupil defect. This shows the normal reaction. Okay, here we have an ambient light. Here's the size of the pupil. Now you shine the light in the right eye, and both eyes constrict. You go over to the other eye, left eye, and both eyes have stayed constricted. So you don't have a relative afferent pupil defect because the eyes are not changing sizes as you swing it back and forth because both optic nerves are working. Now you go over to an afferent pupil defect in the left eye right here. Well, the pupils are a little bit bigger because those little black boxes in the pretectum are getting less light, so your pupils are going to be a little more dilated. Now, here's the relative afferent defect here. Say it's in this left optic nerve. You go over to the good eye, they both constrict, no problem. Then you go to the bad eye, and this eye will get bigger. So as you swing this pen light, between the two, you're going to go constrict larger, constrict larger. Again, it can only happen if you have a lesion in the eye, in the retina, more than 50%, or in the optic nerve. Now, here's an efferent defect. You're sitting there and you're looking at the left eye. It's big to begin with. Well, why would it be big? Because you have a problem with the third nerve. Okay, now don't forget the third nerve that's parasympathetic. It's normally going to want to constrict your pupil, and because you've lost that, the sympathetics have taken over, so it's dilated. Okay, now you can see there's just no way if you've got that third nerve damage that you're ever going to constrict this pupil. Okay, so this is an efferent defect. Okay. Now, what do you think this is? Well, it looks to me like a problem. In the optic chiasm, maybe. Well, we call this bitemporal. Remember, you always define it by the loss. Bitemporal, heteronymous hemianopsia. Now, would you have a relative afferent pupil defect here? Well, same amount of light's coming in on both eyes, so you wouldn't have it. In this particular case, we'd have a contralateral or a right homonymous hemianopsia. Right homonymous hemianopsia. Now, but look, I was wrong. It's only the lower quadrant. It's only the lower quadrant. So where does this have to be? If we were in the lateral geniculate body, it'd be the whole thing. It'd be a contralateral or homonymous hemianopsia. But you can see we're only getting the ventral quadrant, the ventral quadrant. Okay, so this has to be somewhere between the lateral geniculate body and the optic radiations. Now the question for you would be, would this be in Meyer's loop? Well, it wouldn't be in Meyer's loop, or you'd have the deficit in the upper quadrant. Now, Greg talked about the hill of vision, okay? And when I look at this, I can see the disc right here, and I can see the disc right here, so I know this is the right eye. The right eye, if the disc's on the right, it's a right eye. And what's happened here, here's the fovea, here's the disc, so it's a right eye. You've got a lowering here in the sensitivity, but you've got a general lowering, uniform lowering here. So I would probably call this cataract, diffuse lowering of the sensitivity. Here in a Goldman plot, I call this a Goldman printout over here. This is a hill of vision Goldman printout. Again, the disc is on the right, all right? And so here'd be the fovea, so it's a right eye, and you can see that this area in here is uniformly less sensitive. So this would be the result of a cataract. When I look at this, I say, oh my gosh, what eye is it? Well, the disc is on the right. Here's the problem, right on the fovea. Disc is on the right here. Here's the problem, right on the fovea. So what are you going to think right here? Well, the main thing I'm going to think is age-related macular degeneration because that affects the fovea. Now you're going to say, gee, the whole thing isn't affected. Well, the whole fovea isn't dead yet. But you know it's the fovea is being affected here. So this would be a right eye. This would be a right eye. When I look at this one, I say, oh my gosh, what eye is this? Oh, gee, here's the fovea. The disc's on the right. It's a right eye. And I got a decrease in sensitivity out here in the periphery. Well, you're going to say to me, well, I'm taking medical neurosciences, and I know this could be, oh, gee, a detached retina, or it could be glaucoma, because Dr. Heatley told me glaucoma normally gets the periphery first. Well, what could you do? You could look at a Goldman printout, or you could test the eye for pressure to differentiate between the two. So in the case of here we have a glaucoma, you know that it's going to affect the fibers out here in the periphery. Okay, again, this is the right eye. Here's the fovea. So it's going to affect peripheral. But remember, in the case of a detached retina, it could go across the horizontal meridian or the vertical meridian. And you notice that these little deficits respect especially the horizontal meridian. And you know that there's some pressure here as the fibers come into the cup through the disc. And you can have little damage here. And usually it's the most peripheral fibers that are affected. But you can see, again, this does not go across the horizontal meridian. So this would be glaucoma. Now you should know this chart. I know everybody probably does. I guess what I'd worry about would be macular degeneration and glaucoma. I think in the past people have confused cupping. Some people have thought that cupping happens with macular degeneration. I'd be careful about that. Cataract now, in the book it says it's a leading cause of blindness in the world, but it's reversible. And it also says that cataract surgeries are the most common, yet Dr. Pasek said ear tubes are the most common, so we'll let those guys fight it out. When you think about age-related macular degeneration, we're going to think about that retinal pigment epithelium, things happening down there, eventually the blood vessels breaking through and going into the retina, causing damage right there at the macula. When you think of glaucoma, you're going to think mainly about too much pressure and pressure right there at the optic disc cup and affecting most peripheral vision. Now, age-related macular degeneration is the leading cause of irreversible severe vision. Okay, this is the second most cause. So I think those are things that you should also know. When we come over here to the relative afferent pupil defect, I think, remember that if you have more than 50% of the retina detached, you're certainly going to get it. If you have the optic nerve, again, a pretty good optic nerve one or a compression, depending upon how much you've damaged it, you have a good chance of getting a positive relative afferent pupil defect. Now, stroke and cataract, no way in stroke. I mean, you're not going to have any problem with your pupillary light reflex if you have a lesion way back in area 17. And it's also going to be negative in these other ones too. So just remember up in here, the further out in the visual system you get out near the eye or the tract is where you're going to get this relative afferent pupillary defect. What else? I think it's kind of interesting that retinal detachments occur more in long eyes. You should know some of these things that people normally associate with these problems. If somebody says, gee, it looks like algae on a general wave, you're going to say retinal detachment. You get cataract, you're going to have people complaining about glare and lights, things like that. So you have some pretty standard clinical associations with these things that you should know. The ear is pretty interesting, so I'll take another swig of Coke. You know that sound comes in, here's the outer ear, and it goes through the ear canal, and then it influences the tympanic membrane in the inner ear, and then middle ear, and then it goes into the inner ear. And what I'm going to do is talk about the outer ear, then the outer ear, then the middle ear, then the inner ear. This is real important for you to know. This is an auditory threshold curve. And I want you to know that the most sensitive sound here is right about 4 kilohertz down here. Okay, very important. The other thing I want you to know is this is conversational speech up here. And as you get older with presbycusis, when you start losing your high frequencies, it's more difficult, and I can attest to this. It's more difficult for you to hear those consonants than it is the vowels. Now, the main point of this is that this ear here is just not, to make you better looking or vestigial or something like that. This ear actually amplifies certain frequencies depending upon their frequency and whether the sound source is up here, here, or down here. And you can see if you put a little microphone out here and record a sound, and put a little microphone in here and record a sound, there are major differences. And what I want you to know is that this line right here is the sound from the recording out here outside your ear, and this is the recording from right here. And you can see that the outer ear, okay, and the ear canal amplify and depress certain frequencies depending upon whether they're level with the ears, below the ears, or above the ears. So it's just not there for good looks. It amplifies, and also, therefore, it's going to help us a great deal in directional location, sound localization. Now, when we move into the middle ear, we're going to talk about the malleus and the incus and the stapes. And remember that when the sound comes in, it's eventually going to go into the fluid-filled inner ear. And so we need this malleus, this incus, and stapes for impedance matching. Now, if we didn't have the malleus, incus, and stapes, we lose about 99% of the energy in that sound coming in. So this helps us in the impedance matching. You should know tensor tympani right here, controlled by fifth nerve, and right here, stapedius controlled by famous motor 7. Don't forget the eustachian tube is coming in here, so you can get lots of middle ear infections, all right, to come up in here, and going to give you a conductive hearing loss. Okay, don't forget, this middle ear cavity can also, infections in here can also give you meningitis by getting into the meninges. Again, outer ear, middle ear, inner ear. The way I think about it is that when this stapes moves, it moves the oval window and causes a traveling wave going down this basilar membrane. Now, sitting on the basilar membrane, you're going to have those hair cells. So as this thing goes in and out, you have traveling waves going down here like this. Now, don't forget, oval window is going to move the fluid in scala vestibuli. All right? And then it's going to come around, and then you have scala tympani down here. It's going to move the round window. So don't confuse the oval window and the round window. And all this is perilymph in here. Endolymph will be in the scala media. Now, if we take a cross section here, we can see the scala vestibuli. Now, don't forget what's going to move this fluid, the oval window. Then we have Reissner's membrane. Then we have scala media, or the cochlear duct. Then we have scala tympani down here, and the fluid here is going to move the round window. Don't forget that. Here are some of your eighth nerve fibers. And then we have the hair cell sitting in here on the basilar membrane with this tectorial membrane on top. And this basilar membrane and the organochord is going to go up and down and be sheared, send information into the central nervous system. Here again is a tectorial membrane right here. The key thing, we got one row of inner hair cells. And then you got 3 rows of outer hair cells right here. All right? Now, as this shearing effect affects this inner hair cell, information goes in the eighth nerve into the cochlear nuclei. Now, don't forget, these outer hair cells are actually being controlled by information coming out the eighth nerve that goes in here. And this information coming out the eighth nerve is coming from the superior olive. Now, I didn't talk about this in brainstem. I talked mostly about the information coming in from the inner hair cells going into the cochlear nuclei, but there's information coming out this eighth nerve from the superior olive that goes in and controls these outer hair cells. So it controls these stereocilia here, which are embedded in the tectorial membrane. So these outer hair cells, and these are the ones that die more often than these inner hair cells. So in presbycusis and other things, you're going to lose these outer hair cells. These are very motile and can change the sensitivity via these stereocilia of the tectorial membrane. It's very important for you to understand. You know from the vestibular system, kinocilium, stereocilia, that this is the way that's going to excite this cell. This is the way that's going to inhibit the cell. Main thing here is that here's your basilar membrane going up and down. So when that oval window that stapes moves that oval window, high frequency sounds are going to cause great deflection down here at the base, like right here. Low frequency sounds are going to cause greatest deflection way up here at the apex. Now don't forget, for a low frequency sound, it's going to have to go all the way through here, but the greatest deflection is going to be up here at the apex. It's going to deflect it a little bit down here, but not enough. So your brain's going to know, because this is going up and down much more than this, that you've got a low frequency sound. Okay, so this would be down here at the base, high frequency, up here at the apex, low frequency. Now, when the information comes in, you already know this, when the information comes in from the hair cells out here, they go to dorsal, ventral cochlear nuclei, then they can go lots of places that you already know. Go to the superior olive, up the lateral meniscus to the inferior colliculus, up to the medial geniculate body, and then think about how they'd get to the auditory cortex. They would go through the sublenticular limb of the internal capsule. And then auditory cortex would be areas 41 and 42. Now don't forget, you got a medial superior olive and a lateral superior olive, and that's pretty important. The lateral superior olive is going to help you in sound localization for high frequencies, okay? It will help you localize a high frequency sound, tell you where it is on the right or left or things like that. But that's mainly for high frequency, LSO, high frequency. Now in the case of the medial superior olive, okay, you're going to use these lower frequencies where you can use timing. So low frequencies, medial superior olive for sound localization. High frequencies, lateral superior olive for sound localization. Auditory cortex would be right here on this, I call it the transverse temporal gyrus of Heschel, areas 41 and 42. Blood supply again would be what? Middle or anterior cerebral? Okay, you should know it's the middle cerebral. Conductive hearing loss versus a sensory neural. Again, if we have a problem in here in the cochlea, it's going to be sensory neural. If we have a problem coming in through here, it's going to be conductive. And don't forget, there's one way of testing this. You can just put a little like a vibrating thing on the mastoid process, and you can bypass this outer ear and the middle ear and actually just turn on these the hair cells in here, and you'll be able to tell different frequencies of the stimulus and things like that. So that would be, if you did have a conductive hearing loss, you could still turn this on, okay, via the impact on the bone if the hair cells are okay. So the Weber test and the Rinne test. Well, the Weber test, say you got you have a patient with a bad right ear, and you do the Weber test, you put that tuning fork right in the middle of the forehead, and what if you know the right ear is bad? So if all of a sudden the right ear sounds louder, then you're going to have a conductive loss. If the right ear sounds softer, then it's a sensory neural loss. Now, if you know that right ear is bad and you go down there and put that little tuning fork right next to it, well, normally you're going to always hear air better. But if you put that, if you have a bad right ear and you put that fork down near the right ear, if it's sensory neural, you're going to hear less sound, but it's going to be air is going to be better than bone. If it's conductive, bone is going to be better than air. Again, let me emphasize these pathways. I think most of you already know these. But when you have a stimulus coming into the cochlea, you're going to have volleys of firing in the cochlear nucleus. So the stimulus comes in, a volley here, a volley here, a volley here. So these are going to all fire together, all together, all together, all together. But of course, this in the nerve will be first, then the cochlear nuclei, then the superior olive. Okay? So again, you stimulate here, you're going to get a volley of electrical activity here, a little later here, a little later here. This is the auditory brainstem response. And you can do this in children because when they're very young, you can get this readout without having them have to cooperate with you during the test. This shows a normal auditory brainstem response. So this one right here would be probably the nerve. This would be the cochlear nuclei, and then you're going to have like the superior olive and the inferior colliculus. So you can see there's a time in here, the time it takes, and also the amplitude. Now here's normal again, so here would be the nerve, and then you'd have things like this would be the cochlear nuclei, then you have superior olive. And you look at these various things here like a tumor, infarction of the brainstem, or an acoustic neuroma, and you can see that different things are being delayed. There are differences in the peaks and the amplitude. You should be able to figure these out by yourself. This shows a normal audiogram. This would be bone right here. This would be by air, and they match up. So this would be a normal audiogram. Now what's happened here, the person's hearing better with bone than they are via air. So this means, what does this mean? If you hear better by bone than by air, that means you have a conductive problem. This one right here, oh boy, there's a little notch here. Look at this notch. And this little notch here is where everything drops down quite a bit here, both bone and air, so it's a sensory neural loss. This little notch here is usually seen in people like Dan Ulrich, who had a lot of loud noises when he was working as a kid out there in Montana, or hunters or people who drill all day, things like that. And this notch is usually around 4,000 hertz, usually just at the end of the first turn of the cochlea. So this is very demonstrative of loud noises, okay? Very loud noises where they have this little notch right here. Sensory neural. This is sensory neural. This is occurring in me right now. This is presbycusis, where we have a general fall off of both bone and air of the higher frequencies. This is definitely sensory neural. And you should know this is presbycusis. Also think about what presbyopia is at the same time.